And we're attending so I'm trying to that's what I'm saying. We're just gonna what I keep getting
Oh, sure. It was on November 10th. I know it's 2 months out, but might not be able to make the class that day. Okay. So if there is anything on that, is there a schedule around it?
Yeah. Thanks for letting me know. I don't remember when our midterms are, but if there's a midterm that day, we can schedule for something.
Awesome. All right. Thank you so much. I really appreciate it.
Yep.
All right. Thank you.
Yep.
I think we're safe. Yeah. Just end up. Was that on board? I heard. Yeah, that was like. I don't think we were put that in celebration. No, he never. Funny how that's. I thought he died from like 2 months. Right, he was talking about something. You got the. No, yeah. You just right, but like, you calculate before you. Remember how we calculate the number of volts for each reactant, and then we input the volts per reactant. So you're gonna use volts divided by 2 to get that value. But you don't. Well, you're telling me that I have to get. I divide that by 2. But I only have to. Yeah, exactly. You on my own or do I find this guess? Yeah. You just say like take 2 and you see how it works. I'll put 1.5 and then just keep changing over and over. I'll tell you, I think it's 1.26. I mean, yeah, that's a range for this. So. And then on your 5th one, you'll. But I will do this probably tomorrow. To pleasure myself. It's like very
It's almost like that's it. Most of them just love it.
Bro, you lost privileges 2 years ago.
Yeah, no, wash that hand before I dab you up.
Your comment, oh, I did not. Yes, and so I don't get notifications when you guys comment on your activities, and so yeah, if it's something important, probably email will be best.
Bro, that was last week. Oh, you didn't work the whole night now. I absolutely love it. You guys trees in there, bro. I didn't go in videos. I'll send it to you. Most of that morning behind. Race once it is. I have That's because like 5 minutes. I feel bad.
Okay, I'll take a look afterwards. Can you send me an email just to remind me to check it?
On Thursday, I might have that in. No, I forgot Buster. Oh, Buster.
Either one's fine. I'll see either one.
It's gonna be. I think it will probably.
I don't wanna dive into there.
You don't wanna die on the right sense that is. Think about it, you're just developing your seat.
So I did that, right? I did everything right on all of them. But when I did the number, I didn't convert it to feet, so I did that in inches. But last equation, I did convert it, so I think it was like just really weird. I did everything right, so get. Yeah, he said 9. He said 9.8. 1.1 step.
Still being.
Your week going?
Good. Good. I've usually I work from home Monday, Wednesday, but my buddy's wedding is this weekend, and I'm a groom, so I'll be out of town actually from Friday until Sunday, and so I've been coming in every day just to try to get as much work done as I can before I leave.
Easter on Thursday.
No, I can't do that.
Little Bobby has.
Dean Susan is 2 floors above me, and so if she sees me. She has very good timing. She like always kind of has a sixth sense for when I'm about to leave, and then she meets me. She's like, "Oh, you're going home already?" I'm like, "Susan, it's 7:30 p.m."
Already part.
Yeah, I know. It's always like I don't know why. So if I leave before then she's gonna know something's up. It's in, well, okay, maybe I won't. It's kind of near the Temecula area, so it's a bit far. Hey, what's up?
What teacher is this? Oh,
Hey.
yeah.
FOS, what do you mean by FOS?
Factor safety.
Oh, yes. All right, it's 5:30, so let's go and get started. All right, good evening, everyone. How's everyone doing today? Everyone's feeling cooler. The sun's not trying to kill us anymore, which is good. But apparently there was a storm. And so on Friday, there was actually a lot of rain in my area. It's like, wow, it's not the sun, it's the rain. So
Yeah, and it was right after the fire, so you got all that like acid.
I know.
from the ashes on your car and
What?
the rain.
Mother Nature just hates us for some reason this year. But anyway, so we survived, so we're here. Okay. All right, so last Thursday we had our activity, and so that means this week is going to be a lecture week. And so I have a lecture planned for today, lecture planned for Thursday. And so, we kind of got into this a little bit already, but we're going to start talking about, some of the application details in FEA. So, we started talking about meshing on last Tuesday, and so we're going to finish up the mesh, probably going to talk about meshing today. And then Thursday, we're going to start talking about boundary conditions. And so, this is kind of the, the nitty gritty on how FEA's simulations are applied for us as engineers. All right, and so, all right, activity 2. So you guys have that out there, and so remember that's due this Friday, and so make sure you guys are working on it. And so remember to scroll all the way down to the end, because there, in addition to the bike crank, there's also the other bike frame problem I want you guys to do as well. Okay, so make sure you kind of do both parts. Okay, and so are there any questions I can answer before we get started for today? Okay. Oh, yeah.
So, I mean, I already asked this question, but I understand. So with doing on the activity, when you said finding the tensile and the compressive strengths, where exactly would we go to find that?
Yeah, so you can assume the tensile and compressive strengths are the same as the other strengths, so about 35,000 psi. But what I want you to do instead, I want you to change the direction of the force. And so for the first test, I kind of talked to everyone around, but the way to kind of get the maximum amount of force with 100 or maximum amount of stress with a 100-pound force is to apply it in bending. And so I believe that was the Y direction. And so to apply a compressive stress would apply it in the X direction. And so then, you would see that if you just by changing the direction of the force, you're going to change the stress profile a lot, because instead it's purely compressive instead of bending. And so what you're going to need to do is that, what you should see is that in compression, if you point that force in the X direction, it's going to require a lot more force in order to get it to fail versus bending, because it's a lot stronger in that direction. Yeah. Question? Am I currently in Star Trek: The Next Universe? Is the audio weird or something? Okay, well, if the audio sounds weird, just let me know. I see. Okay. Oh, okay. I see. All right. Okay. All right. So let's go ahead and get started today then. All right. So let's kind of pick up where we left off, talking about meshing basics. Okay, and so last time we talked about meshing, we talked about kind of what I call kind of the principal trade-off when you're choosing your element size. Okay, and so the trade-off that we often are thinking about in FEA is a trade-off between accuracy, or how accurately our FEA simulation represents reality, and cost. And so if you remember from last time, if we have smaller elements, and so the smaller our elements are, the more accuracy that we get. Okay. Whereas for cost has the opposite kind of scaling, where we want the least amount of elements possible, because the less elements there are, the less number of elements, the less cost that we're going to incur. Okay. And of course, by cost, what I mean is oftentimes it's going to be time. And so it's going to be the amount of time your simulation is going to take. But once you start scaling up into kind of the really kind of massive FEA simulations, that cost could also mean computer memory. It could also mean power. And so the amount of electrical power that's used to run the simulation, which I think normally you don't really think about. But if you kind of know anything about mining crypto, the cost for performing a mining operation is real. It's why a lot of companies are really cracking down on crypto mining, because it's just sucking up so much power from the country's grid. Okay, but for the types of simulations that we run, usually it's time. So time is the cost that we're associated with. Okay, and so of course these two goals are at odds. So to get an accurate simulation, you got to pay more. If you want to have a cheaper simulation, then that comes at the cost of accuracy. So there's no way to kind of really satisfy both of these in absolute sense. Okay? And so that's why we call it a trade-off. And so a fair question to ask is, how do you know when you have enough accuracy? How do you know when you have enough elements in your mesh? And that's kind of the intuition that I want to kind of impart on you guys is that, it shouldn't be a contest of how many elements you can get in your mesh. It should be, what is barely enough such that I get the accuracy that I need. Okay. And I think even like a lot of professional FEA people kind of get this mixed up because sometimes it kind of becomes like who has the bigger fish. It's like, oh, I have 15 million elements in the mesh. Oh, I have 25 million. It's like, who cares? It's just whoever can get the most accurate result in the least amount of work. That's the one that you want. Okay. Oh, question. So why do we care so much about cost? Don't we want an accurate simulation? So isn't accuracy something that trumps cost? That's a great question. And so, you definitely do want to have as accurate of a simulation as possible, right? But you want it to be just accurate enough, right? And so what that means is it kind of different for every application because sometimes, for, say like you're designing something with very, very small tolerances. And so you're going to want to estimate the stress within, up to, the fifth decimal point with perfect accuracy. Okay. And so in that case, then you have to, really make sure that your accuracy is up there. But if you're doing a situation where you're working with a simplified geometry anyway, and you're just looking for just an approximate solution, then you can get away with a less accurate solution just because, you're not really looking for something, super, super accurate. Okay. And so that's kind of this notion of enough, right? And, later on in the class, we'll get into all the different things that can affect accuracy because mesh isn't the only thing that can affect accuracy. But one way that you can test if your mesh is accurate enough is to run what's called a mesh convergence test. Discuss what that is right now. Okay. And so ideally, you want to reach a point when, if you ran your simulation on a certain mesh, if you refine the mesh anymore, or if you make the elements any smaller, you don't see any change in the solution. Okay.
What power usually?
You mean for the change?
Yeah.
It depends on the application. So usually, for I'd say general use, if the change is less than 1%, then I'd say that's pretty converged.
Oh, it's based on percent.
Yeah.
The accuracy.
No, yeah. So usually it's a percent of how much the quantity is changing. Yeah. Mhm. Because for most situations, you're going to have something like this. Okay? And so a mesh convergence test can be summarized in a kind of in a line chart like this. Okay? And so usually what we have, there's multiple ways that you can display it. Some people put the element size on the x-axis, but for me, I've always learned it as a number of elements, and so that's what I'm going to do. That way you kind of get convergence off to the right, which I think is more natural. And on the y-axis of this graph, you're going to have a quantity of interest. And so what that quantity of interest in is, again, is going to depend on your application. But a lot of times this is going to be things like the stress, either the average stress or the maximum stress in your simulation. Or it might be a deformation. And so it really depends on kind of what you're principally looking for in your simulation. Okay. Usually you use stress because stress traditionally is a lot harder to converge than deformation. And so if you can get stress to converge, then you know for sure that deformation is going to be converged as well. And so most of the time, what you're going to do is and so the way a mesh convergence test works is that you're going to take your simulation, you're going to take your model with the boundary conditions that you specified and run that exact same simulation at various mesh densities. And so you're going to start with a fairly coarse mesh, okay? So let's say that you start, right here, okay? So you ran the simulation with a very coarse mesh, let's say that you just have a few hundred elements and you measure the stress, the maximum stress in your object, and it's like that, okay? From there, what you can do is you refine the mesh. And so you lower the element size and you rerun the simulation, making sure to change nothing else. And so everything else in your simulation is the same. The only thing that's changing is the size of the elements in your mesh. Okay? So let's say that you ran the simulation again. You compute your quantity of interest, and you can see that it went up a little bit. Okay? And so at this point, because you had kind of such a significant change between data points, we say that the mesh isn't converged yet, because what we expect is that if we keep continuing this, and so if we ran another simulation at an even finer mesh, your quantity of interest is going to change again. Okay? And so you keep doing this. And for most cases, you're going to get a situation that looks like this. Okay? Eventually, once you kind of reach a certain point, then this curve here is going to plateau. It's going to level out. Okay? So each data point okay. Each data point is a simulation run at a different mesh density. And as you go from left to right, your mesh is going from coarse to fine. Okay, so you're adding more elements, all because you're making the elements smaller. Okay. And so most of the time, except for some special cases, you're going to get a curve that looks like this. And so eventually, you're going to reach a point. So let's say that kind of right here. So if we consider this point right here, right, if we refine the mesh even more, and so let's say that we're at that point and refine the mesh, our simulation value is not really changing. Our stress value is not really changing. And so one way that we can interpret this is that as we go from here to here and here to here, okay, because the number of elements is increasing, we're incurring more and more cost as we go to the right on this curve. Okay. All right, so we're incurring more cost because our number of elements is increasing, but we're not really getting any benefit from it because we're not getting any more accuracy. And so we kind of reached the peak or the pinnacle of accuracy. Okay? And so what we can conclude, therefore, is that once we've kind of reached this point, this mesh right here, we say that this is the mesh convergence point. And so this is kind of the best, or kind of the mesh where we get enough accuracy for the cost that we're incurring. Okay. Right, so this is kind of the idea with the mesh convergence test. And so the idea is that you don't really know beforehand how much mesh density you need. I think even the most experts of experts can't look at something like, I need 1 million elements for this, right? That's impossible. And so the way that people prove that their mesh is good enough is that they run a mesh convergence test like this. Okay, and you can run this for any FEA simulation. So you can even do it for activity 2 if you want. I think for activity 2, you'll reach convergence very, very quickly. So it might be a very boring mesh convergence test. Okay. But this is kind of the most basic way of how people prove that their mesh is kind of well converged. Okay. And so whenever you read kind of a scientific paper or you read any kind of technical document that involves an FEA simulation, a mesh convergence test like this is almost necessary, I think. Otherwise there's no way for you to prove that your mesh is converged. And so DJ, kind of coming back to your question was fantastic, by the way. And so, coming back to your question, yes, we want to have as much accuracy as we want, but we don't want to incur unnecessary costs. Because after a certain point, your mesh is going to converge, and adding more elements to it is not going to improve your accuracy. It's just going to be kind of a waste of time, a waste of power. Yeah. All right, so we'll come back to mesh convergence testing. It is something that's very important, and so it's going to be a part of your projects. I don't know if it's going to be part of your midterm project. I need to double check, but it's definitely going to be part of your final project. And so, this is something that you're going to be doing. I think just because in my opinion, I think it's necessary whenever you run any kind of simulation, and it's also kind of a good knowledge to have in general. Okay. But I'm bringing this up now, and I didn't plan to originally because I think without this explanation of cost and accuracy is kind of very nebulous. It's kind of very qualitative in a sense. But hopefully with this mesh convergence test, this kind of illustrates a bit more kind of what we're looking for in the mesh in terms of accuracy, and sometimes adding more elements does not actually make your simulation any better than before. All right, any other questions on this? All right, so let's talk about element shapes. Okay. And so as you've probably noticed in our activities, not only can you decide the size of the elements or how many elements that you have in your mesh, but you can also decide what shapes the elements are going to take. And of course, probably as you might have probably guessed, the shape that you choose for your elements will have an impact or have an influence on your results.
Would it be the same size? Would it still cost more in terms of the on like a triangular shape compared to a square shape?
Yeah, it's a good question. And so, we'll talk about it in a bit, but basically, for most cases, if you can get like a rectangular shape mesh on your FEA simulation, it'll run the calculation faster because it can fill the space a lot more efficiently. So you're going to end up with less elements and less nodes, but it's going to be a higher quality solution because the rectangle is a higher quality element. Yeah. And so if you can, rectangular elements are good, but there are situations where you're going to have to use triangles. I think some people actually experience that with activity 2, which I still don't know why, but for some reason, it's either some computers or maybe it has to do with your fingerprint. I don't know. Where sometimes specifically for activity 2, people can't run rectangular mesh for some reason. I still haven't really found out why. And so, just as I've alluded to, there's kind of two kind of broad categories of element shapes, at least in terms of the basic shapes. Okay? And so the two categories are your triangular elements and your rectangular elements. And they each have a version in 2D and in 3D. All right, so in 2D, the triangular element is a triangle. Very groundbreaking, I know. And so you saw that in activity 1. So activity 1, you ran a mesh, or I had you guys run a mesh with triangular elements. And so you kind of saw this. In 3D, the triangular type element is known as a tetrahedron. And so if you play Dungeons and Dragons, your tetrahedron is basically your 4-sided die, or your D4. Okay. And so it's a pyramid with 4 sides. And so, the hidden edge that you don't see here kind of just goes kind of straight, just like that. Tetrahedron kind of sounds like it would be a bad guy in like Stranger Things or something like that. But it's just the name for a 4-sided pyramid. Okay, so now we go to the rectangle. And so the rectangular element in 2D is a rectangle, groundbreaking, but then we often call it a quadrilateral. And the 3D version of a rectangular element I like to call it a brick because it looks like a brick. But its technical name is a hexahedron. Okay.
All equal lengths, right?
Doesn't have to be, no. No. And so all these elements can kind of skew. And so the key characteristic here are just the number of points and the number of faces and the number of edges. Yeah. But these boxes can be distorted based on your geometry. And so the reason it's called hexahedron is because hex means 6. And so a brick has 6 sides, just like a dice, just like a box, just like that. Okay. Okay. And so what's the difference? And so, when will we use one or the other? Let's talk about triangles first. And so triangles have a very, very useful property in that they can mesh any geometry without fail. Okay. And so there's actually a very sophisticated and very lengthy mathematical proof of this. And it's basically, and so if you want to look it up, it's called the simplex property. Okay. And so the simplex property basically allows them to fill any space. Okay. And so, we're not going to go through that proof because I think that would take an entire lecture. But basically, the idea is that with the triangular elements, they kind of have this kind of lopsided look to them. So they're not perfectly even. Okay. And so, if we look at kind of this triangle right here, we kind of just look at it from kind of head on. We have one side that's kind of like a thicker side and one side which is a thinner side. Okay. Right, I know that perspective changes depending on if you rotate the triangle, but the idea is that you have kind of this asymmetry in its shape. Okay. And so that asymmetry really helps it fill in all the little kind of nooks and crannies of any geometry. Okay. And so that may not sound that impressive, but if you use finite elements, for all kinds of weird geometries, this property just is super clutch because, if you are, especially if you're developing a very sophisticated geometry in SolidWorks, and you want an element that's going to be able to fill that geometry without fail, triangular elements are going to have your back kind of no matter what. Okay, so on the other side of the coin, we have the rectangular elements. So what's good about rectangular type elements is that they can fill space very efficiently. Okay. And so the amount of triangles that it takes to fill in a space is always going to be more than the amount of rectangles it's going to take to fill a space. Okay? And so if you think back to activity 1, and so in activity 1, I had you guys redo the activity with triangles. What you should have seen is that the triangular mesh had a lot more elements and a lot more nodes than the rectangular one, because the rectangles are just way better at filling space efficiently. Okay. And it just so happens, and we just got done talking about mesh convergence, rectangular elements have much better convergence properties than triangles. Okay. Okay. And so what I mean by that is that you can reach mesh convergence with a rectangular mesh much faster with much less elements usually than a triangular mesh. Okay. And of course, that's very attractive because if you can get a rectangular mesh, then you can run your simulation, you can get accuracy with much less cost, which is always going to be a plus. Okay. Okay. And so for that reason, the fact that you can get a higher quality solution with rectangular elements for less cost, if you can get rectangular elements in your mesh, that's generally going to be a good thing. Okay? And so rectangular type elements are generally preferred when possible. Okay. But the key there is when possible. Okay, and so there's definitely going to be situations. Some of you have experienced that already, when ANSYS just refuses to mesh your geometry with the rectangular type element. Okay, and so in those situations, you're going to have to go back to the triangular ones. But at the same time, that's not the worst thing in the world. And so before I actually started working here, when I was doing all my graduate work, I did all my simulations with tetrahedron meshes, and so and I've got great results with that. And so using a tetrahedron, if you have to use tetrahedron mesh, it's not the end of the world. You're still going to get really good results. You just may have to use a smaller mesh size than if you use a rectangular mesh for it. Okay. And so there are differences between the two, but there are ways primarily by adjusting the element size you can get good results no matter what element shape that you pick. Okay. But I did want to let you know the difference between them and you know what the pros and cons of the two are. Okay. Any questions on this? Okay. All right, and so that's element shape. Okay. And so the next thing I want to go over is this idea of skewness. Okay. All right, and so when you give a CAD model to a finite element software like ANSYS, right, and you ask it to mesh, you know what the software is going to do is that it's going to try to fit all these little elements into your CAD model as quick as as efficiently as possible. Okay. In order to make sure that your original geometry is respected, or in other words, you don't get some kind of cursed or scuffed version of your geometry, oftentimes your elements are going to have to distort themselves in order to fit within the geometry. Okay? And there are ways that you can loosen this, but basically what the default in ANSYS that if you give ANSYS a CAD model, it's going to reproduce that geometry with your mesh exactly. So the idea is that if you overlay kind of your finite element mesh and your SolidWorks CAD model, there should be no difference between them. So you should get kind of perfect overlap. But because of this, because you kind of are striving for perfect geometric accuracy, there will be some situations where an element will have to distort itself in order to kind of fit within an awkward space. Okay. I wrote that already. Okay. And so let me kind of draw an example for you. Okay. So let's say that we have kind of a curved edge, and so this is kind of where it kind of occurs most often. And so let's say that we have a triangular mesh on this. Okay. And so let's say that we have a triangle here. Here, and then triangle here. And so you can kind of already see, as I'm drawing this mesh, it's not because I suck at drawing, although I do suck at drawing, but you can see that, just kind of naturally as I'm trying to fill this space efficiently, all the triangles are kind of a little bit different, right? And so they're all kind of approximately the same size. At least I tried my best to be. But but if you compare, the lengths of the edges of one triangle to the next, there's no two triangles that are perfectly the same. Okay? And in the extreme cases, you might get elements that are extremely distorted. And so, you might get a triangle that looks like this. Pretend those lines are straight. Use your big brain imagination, okay? And so, actually, I can do a better job. I'm not that desperate. My wife and we've been hanging pictures in our house lately. And the level has been, I hate that thing so much. I can never hang a picture straight.
You gotta get one of the laser ones.
Yeah.
So much easier.
No, but then I'll hang it and I'm like, that looks straight. And my wife will put the level and she's like, no, You messed up. Take it off, drill another hole.
Or you start with the thing and tape first, and just then look at the tape, and then if that tape, that strip that you put down is level, then you put the picture print up
I should-
against it.
I should do that instead of drilling tons of unnecessary holes in my wall. All right, anyway, commiserating aside. Okay, so you might end up with an element here that's very distorted. And distorted elements like this are actually really bad for your solution. So, we talked about, convergence properties of different shapes, okay? So those are general convergence properties for triangles versus rectangles. But, even among triangles, even among rectangles, what can happen is that if you have a lot of skew elements like this, it's going to kind of ruin your convergence and ruin your accuracy. Okay? Okay. Right? And so how can we tell, or how does ANSYS measure, how distorted our elements are? And so ANSYS measures this with a metric called skewness. Okay? Or I shouldn't say just ANSYS, but any finite element software will do this. Okay? And so what you can do, and I'll show you how to do this in activity 3, there's a way for for ANSYS to check the quality of your mesh. Okay? So that's how ANSYS kind of describes it. So a high quality mesh will have elements that are not skewed. And I will say that, because the geometries that you're putting in, unless the geometry that you put in is a perfect triangle or it's a perfect rectangle, a perfect square, some degree of skewness is unavoidable. And so it's impossible to get a perfectly unskewed mesh. And so you're always going to have some degree of skewness, but the idea is to hopefully you don't have too much of it. Okay? And so the way ANSYS measures skewness is that it gives you a score. So it gives you a score between 0 and 1. Okay. And so a score of 0 means that the element has very little skewness and is high quality. Okay. Whereas a score of 1 is the opposite. And so now the skewness of 1 is very high skewness. And so ANSYS, after you produce your mesh, ANSYS can assess every single element in your mesh for skewness. Okay. And so, if you have like a mesh with 15,000 elements, all 15,000 elements will have a skewness score between 0 and 1. Okay. And so, of course, it's hard to kind of view that information for all the skewnesses for all the elements at once. And so ANSYS will usually report this to you in terms of aggregate quantities. And so there's a very easy way for you to look at the maximum skewness in your mesh. You can look at the minimum skewness as well as the average skewness in the mesh. Okay. So of course, the question is, what skewness should you be aiming for? So, should you try to have your skewnesses, is having a skewness of 1 bad? What should your average skewness be? Should it be, around 0.4, right? And so unfortunately, as with a lot of things, in this class, it depends on the application, right? So it's going to depend. But, there are some kind of general rules of thumb that you can use for, just for kind of general purposes. Okay? And so I'll say there's no. And so I, these rules of thumb are kind of based on what I've seen, from this class and from my graduate students too, who have used ANSYS. And so generally, for at least for the activities that you're going to be doing this class, these are kind of in the ballparks of where you're going to be. And so, generally your max skewness if you can get your max skewness to be less than 0.8, that's usually, that sounds bad, but that's usually, in a good place to be. Okay. Remember, the maximum skewness could be just one element. So if you have just one element that's just really skew, then it's gonna drive up your maximum skewness score. But oftentimes it is just 1 or 2 elements. Okay. And so if you have a max skewness less than 0.8, that means your mesh is going to be pretty good. Okay. Okay, so next thing you should be looking at is the average skewness, and so that's the average skewness of your mesh. And so if you can get an average skewness that's less than 0.6, okay, that's usually pretty good. Okay. And then your minimum skewness should be around 0. Okay. And so ANSYS should be able to produce at least one perfect element in your mesh. If it can't, then something's wrong. Okay. And so what do you do if your skewnesses are too high? So usually the best way to solve for skewnesses is to adjust the element size. And so if your skewnesses are high, usually that means you need to reduce the element size or increase the number of elements in your mesh. Okay. Because as you can imagine, if you make the elements smaller, then it's a lot easier for them to squeeze in without having to distort themselves, overly too much. Okay. And usually what it is that, you only have to really refine your elements in a particular problematic area. So oftentimes if you have a CAD model, there's just that one region in your model with a very challenging geometry. And so oftentimes if you have high skewness, a lot of times it's because of that one area. So if you just refine the mesh in that area, then you can kind of address some of the skewness issues that you're having without having to go kind of crazy and really blow up the cost of your simulation. And so of course, you know, this is one of the things that kind of gets better with practice and better with experience. And so it's kind of spotting where you think the problematic areas are going to be, and then adjusting your mesh according to that is, you know, something that's going to take experience. All right, question. So could you also go and change the geometry surfaces, like smoothing out curved surfaces to make the surfaces better? Yeah, that's a great point too. And so yeah, another option you can do is to what I call simplify your geometry. So some of the problematic areas that I was talking about often happen towards sharp edges or where there's kind of a lot of finer details. And so if you can adjust your CAD model to kind of eliminate those details and kind of smooth those out, then that's going to help with your mesh quality significantly. And so, you know, I think once we kind of get into the project, once we get into some of the later activities, you know, what you'll see is that a lot of CAD models aren't really designed for FEA. And so what I mean by that is that they contain a lot of these kind of finer details that, you know, may look great in the CAD, you know, and it makes for a beautiful CAD, but it only serves to just make your FEA more complicated. So if you can get kind of a simplified version of it without sacrificing kind of the accuracy of the geometry, then that's going to make your FEA a lot easier. Yeah, that's a great point. Mm-hmm. All right, any questions on this? Okay. All right, so next let's talk about element order. Okay. So this is definitely something I've punted off for a while, but now it's time to actually discuss what this means. Okay. And so if you've noticed from activity 1 and 2, you know, you can you have the ability to change what's called the element order of your mesh. Okay. And so what does that mean? And so you know, the element order is basically the order of what I call the approximating polynomial. Okay. Okay. And so just as you understand kind of polynomial orders as either linear or quadratic, you know, it's the same sense here. Okay. And so let me write out kind of the functional form for a linear element order and a quadratic one, because those are the two main ones that we use. And so for a linear order, our approximating polynomial looks something like this. And so here I have a generic linear function. And so I basically have just AX is equal to B, except instead of B, I have A1, okay? And so the most generic linear polynomial is just a constant term and a term with an X, okay, which is a linear term, where A0 and A1 here are just arbitrary constants. And so, you know, their values here aren't that important. They're just arbitrary coefficients. Okay? And for a quadratic element, you know, we have an arbitrary quadratic function. So we have u of x is equal to a0 plus a1x plus a2x squared. And so this is quadratic. Okay. And so it's the same as the linear order, except we have that additional quadratic term at the end. Okay. Okay. And so what the heck does this even have to do with FEA, right? So why are we looking at polynomials? And so the way that FEA works and the reason it can solve these complex differential equations is that FEA assumes the functional form of the solution before it actually solves it. Okay? Right, so even before it even looks at the differential equation, FEA is going to say the solution to this equation is going to be a linear function, okay? Which of course is highly unusual. So, I don't think you've done probably anything like that in any other class, right? And probably, in most traditional ways in which you solve an equation, you just solve it first, and then just whatever functional form the solution is, that's just what it is, okay? What FEA does is that it assumes this form of the solution first, then it finds the best function of that form that solves the equation. And so, if you've used Excel before, you might have seen something similar. Okay? And so in Excel, there's a function in Excel called a best fit curve, right? And so oftentimes if you have a lot of data, let's say you've collected data from an experiment and you have kind of a lot of data points, they're kind of scattered around like this. Okay? Oftentimes in Excel, you have all these data points, but you want to fit them to a line, right? And so oftentimes you ask Excel, say, give me the best linear function, or give me the best, quadratic function that fits within these lines. Okay? And so, you might get something like that, where this line right here, this is the best fit. And so FEA it's actually quite different, but the idea is the same. So the idea is that you have this, instead of data points right there, you have this complicated partial differential equation. And what you want to do is that and FEA is like, this equation is too hard to solve. And so what I'm going to do is I'm going to assume the function looks like a linear function and just find the best linear function that solves this differential equation. Okay. And so that's what's meant by order. And so when you're choosing the order of your FEA element, what you're choosing actually is the form of the solution, the form that the solution is going to take. So it's either going to be a linear function or a quadratic function. That's in essence kind of what you're choosing. All right. And so how does this affect your results? Okay. And so, whether your solution looks like a linear or quadratic function, of course, you would think that it would have a big impact on your results. And the effect that element order has on your results is actually pretty far reaching. And so it affects kind of a lot of aspects of your results. But I think the first thing that I think to understand is to kind of go back to our concept of cost and accuracy. Okay. And so generally speaking, linear elements will be less costly. And so there's less for the FEA to solve for linear elements. But you don't get that for free, and so the lower cost also comes at the expense of lower accuracy as well. Okay. And if you have a lower accuracy element, that means it's going to take longer for it to reach convergence. And so, if you use linear elements, you sometimes you really need to pack in a bunch of elements in there in order to reach convergence, okay, which is ultimately kind of the goal for this. Okay. Quadratic elements, on the other hand, Quadratic elements are going to be more expensive because they have more to compute per element. But that extra cost that you're paying for quadratic elements kind of pays off in kind of better accuracy and better convergence properties. Okay. And so at its core, that's kind of a good trade-off to remember is, linear versus quadratic. Okay. And so you might be asking, what's the difference between, between changing the element size versus changing the element order, right? Because it all kind of seems to come back to this idea of cost versus accuracy, right? And so if you want to get a more accurate simulation, you kind of have two different options that you can do. You can either make your elements smaller, okay, and so you kind of go back to the element sizing argument that we started with today, or you can increase the order. And so those are the kind of two. And so you wouldn't be wrong. And so both of those are options for you to increase the accuracy of your simulation, and they're called different things. And so I won't test you on this just because it's kind of more FEA trivia. But if you want to increase your accuracy by decreasing the element size, oftentimes that's called H-level refinement. Okay? But if you want to increase the accuracy by increasing the order, that's called P-level refinement. Okay, so P stands for polynomial. H kind of stands for the element. That's kind of the variable that we often use to define element size. Okay, so H refinement and P refinement. But the thing with element order is that it kind of goes a bit deeper than that. Okay, so it's a bit more than just accuracy and cost. It also affects kind of the quality of some of your derived quantities. And so what do I mean by derived quantities? And so there are a lot of results, a lot of FEA solution quantities that require taking derivatives of the primary solution. Okay. So one very common example of this is stress, right? So equivalent stress, principal stress, they all require the derivative of the deformation solution. Okay. And so what's typically done in these situations for your FEA is that the program will compute what I call kind of the primary solution variable first. And then from the primary solution value variable, it'll compute all the derived quantities. Okay? And so for a structural simulation, the primary solution variable is the deformation. So deformation is like the first thing that ANSYS will solve for. And then based on the deformation field, or based on the deformation solution, it will then compute things like the strain and then the stress, and then, you know, all things like that. Okay. And so every type of equation has a primary variable. And so if you look at a thermal situation, you look at the heat equation, temperature is your primary variable. If you're looking at fluids, then velocity and pressure are your primary variables. Everything else is derived from the velocity. Everything else is derived from the temperature. Okay? And so for structural, the primary solution variable is deformation. Okay. And so why is this important? And so, you know that when you take derivatives, it reduces the order of a polynomial by one, right? And so if you have a linear function, okay, you take the derivative of a linear function, what's kind of one level down from a linear function? It's a constant function. Similarly, if you take a quadratic function, you take the derivative of a quadratic function, and you go one level down, you end up with a linear function. And so, if you have a situation where you're going to be computing the derived quantities, or if the derived quantities are a big part of your equation itself, you oftentimes want to have the maximum amount of accuracy for your derived quantities. Okay. In particular, you want to avoid this situation. Okay. And so if you were to use a linear order or a linear mesh to solve for a structural equation, that means your stress field, at least within an element, within a single element, is going to be constant. Okay. So if we draw kind of a mesh like this, well, I only draw just a few triangles. And so if you were to have a linear mesh, that means the stress in this element right here is going to be all constant. Okay. Because the derivative of a linear function is a constant. And so the only places where you see variations in stress is if you jump from element to element. Okay, so that element's going to be one stress level. This element's going to be another stress level right here. That element's going to be another stress level right there, and so on and so forth. Okay? And so you want to avoid these situations because if you have constant stresses in your elements, that can lead to some pretty inaccurate results. Okay, and in the worst cases, you might have something called shear blocking. And so shear locking is kind of a very kind of specific thing that happens in structural simulation only, where if you use linear elements for a structural simulation and you don't, and your elements are a little bit too big, what can happen is that the elements can kind of lock up and they kind of, and the deformations that you get are going to be much, much lower. Okay. And so for these reasons and and more, generally speaking, most of the time you're going to want to use quadratic elements. Because really for you as the user, there's really no big cost associated with it. And it's not something like the meshing element shape where you can't, there's some situations where you can't use quadratic. You can always use quadratic. And so, for those reasons, just to make sure that you have a smooth, accurate stress field and to avoid kind of big problems like shear locking, generally speaking, it's better to use quadratic. Okay? It used to be, and so, from my own background, again, since I never used quadratic elements before I actually started teaching this class, before I started working here. And so the codes I worked on before only use linear elements. But the only reason I used linear elements back then was because quadratic elements are much, much more difficult to code. And so, when I was coding the finite element software I was using in grad school, it was just way easier just to program linear elements and just refine it enough to make sure that it works. But for ANSYS, it's a software that you're using, you're paying to use from a company, and they've gone through the trouble of implementing quadratic elements. And so, if you're using ANSYS, there's kind of no reason not to use quadratic, because it's just so much better, because it avoids a lot of issues that you can get with linear elements. Okay. All right, any questions on this? Yeah. Yeah, great question. So there are definitely higher order elements that are possible. ANSYS doesn't have it by default, but there are ways that you can kind of modify it to. You can use, ANSYS has kind of a scripting kind of thing where you can kind of modify some parts of the code to add higher elements. Most of the time, though, you're not going to want to use higher order than quadratic, mostly because a lot of the differential equations that we look at in engineering are second order differential equations. So things like heat equation, things like Navier-Stokes, things like the structural equation. The highest order derivative you see there is 2. But if you're going to do things like electromagnetics, which have like a 4th order derivative, then those would be reasons where you want a 3rd order, 4th order polynomial. Yeah, good question. Okay, one last point I'll make before we go. Another point for advertising for quadratic elements. Another nice thing about quadratic elements is that if you have kind of rapid changes in the solution, and so over a short period of time, and so maybe you're going from just a short distance and your stress is changing by a lot, quadratic elements can handle those a lot better. Okay. So this is just kind of another reason to use quadratic. And so you might be asking, why is it that you even have the option to do linear? Well, there are certain equations where using a linear element isn't as bad as using structural. Notably, the heat equation and actually the fluids equations, just because of the way those equations are structured, linear elements, they're definitely inferior to quadratic, but the drop off isn't nearly as severe. And so, in those situations, you might choose to use linear elements just because it's going to be cheaper in those cases. But there's a lot of nuance, and there's a lot of things that we can either, we have two ways, and so we can either dive really, really deep into the theory, and I can really show you from a mathematical point of view why linear elements are okay in the heat equation or not, or it's something you just kind of learn by experience and by trying it out. And so I think with the nature of this class, where I've kind of pushed it a lot more towards ANSYS, a lot more in the past, we're kind of go down that route. So I think for those reasons, it's important to kind of know the general properties, which is kind of what we talked about today, and then for you to kind of try it out and experience it firsthand, and so you can kind of see those trends happening. In real time. All right, any final questions before we wrap it up for today? Okay, all right, so that's all I got for today. So thank you everyone for coming today. It's no longer burning hot outside, but still take care of yourselves. Make sure everyone gets good sleep and you're eating 3 meals a day and all that good stuff. Okay, and so I'll see everyone on Thursday.
Thank you.
Sure. What's up, Charles? Getting an error. Okay. What's the error?
Well, there's a lot of them.
Are they, can you type it out? It looks like the audio is really low right now. I can hear you talking, but I can't hear what you say. Okay. Do you want to share your screen? Let me stop recording for a second.